Okay, so our next question is, let me move this a bit to the top. Our next question is, explain one reason for using Unicode rather than ASCII to encode languages other than English. As always, pause the video and come back for the answer. So you can simply answer this saying, let me write the answer here. Why do we use Unicode other than ASCII for encoding languages? So ASCII can cover all the characters of a language, like the English language, like we know, like the symbols. We know there are printable characters. We know there are control characters for the ASCII table, right? But the problem arises when you start talking about other languages, okay, such as that does not have like basically non-Latin characters. So when it's English and when it's Latin, um, ASCII can represent that easily. But when it comes to other languages, other than these two that I mentioned, you are going to need something else like Unicode. So this is how we can say it. So I'm going to say it in the way, there are multiple ways you can phrase your sentence, but you got to try and get the main idea here. Um, so one reason why we would use Unicode rather than ASCII to encode languages, because Unicode um, can represent all characters, symbols from all of the major languages. Okay? And you can also say that it does this. Um, so I'm kind of, my lines breaking over here. I'm not going to the dotted line because I'm using the type tool. So you guys feel free to. Obviously, you're going to write on the line on the dotted lines when you want to change the line. In fact, I can do this right now. Click off of it, and I can increase the line spacing. Inshallah, that should work for us here. It does this by increasing the number of bits to accommodate more characters. Okay, you can say this in a more easier way. You can a number of bits to represent more characters. You could say represent more characters. So you can also mention here something like the ASCII code is going up to 128 characters because you know how many characters we just did that in the previous question as well, 128 bits. So by increasing the number of bits more than 128 from ASCII to represent more characters. Okay, so you could answer this in this way. Now I'm going to share the answer key with you here, and you can then compare your answers. Now remember, you'll get like 2 marks for this. So you'll get 2 marks for this. Here's the answer key. Here's the answer key. It says award up to 2 marks for a linked explanation such as all of the major languages symbols, characters can be represented by Unicode. You'll get one mark for saying that because it uses a minimum of 16 bits. Okay, that's the minimum that it uses, and it uses basically more. You could say 16 bits, you could say more bits, you could say 32 bits. If you don't remember any of this, you could just say more bits, what we have done here. And I have done that intentionally because you don't have to remember this for answering this question. Uh, Unicode can represent all characters, symbols from all of the major languages. Does this by increasing the number of bits more than 128. So we also incorporated 128, showing that we remember how many characters the ASCII code can represent. Okay, so simply, guys, ASCII code has 7-bit, 8-bit. Okay, we first have in ASCII we have the 7-bit standard ASCII code. And then we have the extended ASCII code, which is 8 bits. It allows us to incorporate 256 characters. But even if it goes beyond this, um, we can then use Unicode to represent even more languages. Okay, so you can see that here in the answer key, they have shared the answer. If it's um, 32 bits, you can have 65,536 characters. Now, you could also say Unicode can represent all characters, okay, because it uses 16 bits, or you could say 2 bytes, or you could say more bits instead of 8 bits. All right, so I think our explanation should be sufficient enough to get the 2 points in this exam, inshallah, in this question, sorry. And let's move on to the next question. Okay, so the next question says, I don't know, I find this blue line that comes in the middle really annoying. So if there's a way we can turn it off. Oh, good. Alhamdulillah, gone now. So convert the denary number, convert the denary number minus 43 to 8-bit binary using sign and magnitude representation. All right, let's pause the video. You guys can solve this and then come back to compare your answer. Okay, guys, welcome back. Hello, can you hear me? Okay, I thought the audio mic's not working. So let's go ahead and solve this, inshallah. So it says sign and magnitude representation. We need to keep in mind sign and magnitude representation is done differently than 2's complement representation. Okay, so let me get my pen out. And right, so firstly, we will draw some columns. Firstly, on the right-hand side right here, we will draw a column for our rough calculations, right? So we'll just write rough work. Right. And over here, we will say convert the denary number minus 43 to 8-bit binary. So simply just convert the sign and magnitude representation of a signed number minus 43 to binary. So firstly, I'm gonna do some calculations. I mean, just for explanation purposes, obviously you guys don't write here. You will write within the box provided, okay? Do not write outside of it. So I'm just, for explanation purposes, I'm writing here. So minus 43, we're going to have to consider this and this as 2 separate things. This again is the sign, and this is the magnitude. This is the magnitude. So we'll just look at the magnitude part for now, and we'll convert the magnitude 43 to, simply, we'll just do that. Don't worry about anything else. We'll convert that to an 8-bit binary. So firstly, we got to write our place values down. So I'm going to start writing here 1, 2, 4, 8, 16, 32, 64, and 128. So I have my place values down now. I'm going to write my binary number now. I need to do 43. So convert 43 to binary. Okay, that's what we're doing right here. So 43. Firstly, we'll ask ourselves, is 43 greater than or equal to 128? No, it is not, so we will say 0 here. Then we'll ask ourselves for 64. No, it is not greater than or equal to 64, but it is greater than 32, so we will include 32. So now we need to, in our rough work, we need to start subtracting this. 43 minus 32. Okay, so take out 2 from 3, you get 1 as a remainder, and you take out 3 from 4, you also get 1 as a remainder. Okay, so we have now 11. Now we have to look for 11. Is 11 greater than or equal to 16? No, it is not. It is not greater. It is not equal, so we will say 0 here. We don't want the 16. Is 11 greater than or equal to 8? Yes, it is. So we will take the 1. We'll take the 8 here. So we will subtract 8 now from this. And we get, you subtract 8 out of 11. What do you get? You get 3. Okay, so now we need a 3. Is 3 greater than or equal to 4? No, it is not. So we put a 0 there. 3 is greater than 2, so we will take a 2. You subtract, I'm going to write this all over again. So 3 minus 2 from here, we will get a 1. So we will now just include the 1 over here because that's all we have left, right? So we will take this. This is our 43 converted to binary, an 8-bit binary number. Now we don't have to forget the idea of the sign, right? We have to include the sign. So now we have to represent this because we are doing sign and magnitude representation. We will just convert this MSB to a 1 in order to have the correct answer. So you'll get 1 mark. This question is for 2 marks, okay? You will get 1 whole mark if you get at least this part correct. But they will give you 1 extra mark if you get the sign value correct as well. So we know how to do this. This is pretty simple stuff, right? Inshallah. So let me delete that. Okay. So, and we gotta get rid of these as well. Demonstration. Right. Okay. So what do you simply do? You just got to convert this to 1. So we got to write that in a nice, neat way, right? Um, um, adding a 1, adding 1 in the MSB, to make the number negative. Okay, you can write this in your own wording, whatever you feel is easy to say, but you gotta give the idea, you gotta tell what step you are following right now. So we will just convert this to a 1. So we converted that to a 1. 1, 0, and then the rest of it is the same. We just made the MSB 1. Everything else is the same. So we'll just copy this down. 1, 0, 1, 0, 1, 0, 1, 1. All right, and this is your answer. Draw like a box around it. I'm not able to draw a really nice box, but you can draw a nice box like that. This is the answer. You can just say answer. Okay, so you should get full marks for this question. Right, let's move on. The next question says, complete the table by adding these two 8-bit binary integers. As always, pause the video and come back, solve it yourself, and then come back for the answer, inshallah. Okay, now that you're back for the answer, let's start solving this, inshallah. So it's a very simple binary addition. We're not even going to go into the carryover here, right? So just a 0 plus 0, and you get 2 marks for this. If you get half of this nibble correct, like the 4 bits here and the 4 bits here correct, you'd get 1 mark for this, 1 mark for this. Okay, for getting both of these correct. But inshallah, we know this is a very simple thing to do. Inshallah, we'll get both marks correct. Okay, so 0 plus 0 is definitely a 0. 0 plus 1. Always remember when you want to solve these kinds of things, um, I'm just drawing it here for your reference. 0, 0 is equal to 0. 0, 1 is equal to 1. And 1, 0 is equal to 2. And 1, 1 is equal to 3. I'm just drawing it here for reference. Don't draw it here yourself. Okay, 0 plus 0 is 0. 0 plus 1 is 0. Sorry, 1. 0 plus 1 is 1. 1 plus 1 is 2. How do you represent 2? We're going to do 1, 0. So we're going to carry over the 1 here, and we're going to put the 0 over down here. Okay, so now we'll say 1 plus 0 plus 0 is 1. 1 plus 1 is 2. So again, we will use 1, 0. So we will use a 1, 0 right here. And then 1 plus 1 is again 2. We'll do a 1, 0 here again. 1 plus 0 plus 0 is simply 1. And 0 plus 0 is 0. So 0, 1, 0, 0, 1, 0, 1, 0 is the correct answer. Okay, that should be, inshallah, correct for you to score um, full marks on this, inshallah. All right, moving on to the next question. The next question says a bitmap image is made up of pixels. An image has 5 colors. Complete the table by adding a unique binary pattern for each color. Each pattern must use the same minimum color depth. So here's the table that they've given us, and they want us to fill out the binary pattern right here. So go ahead, try and solve this on your own, inshallah. Pause the video and come back for the answer. Okay, guys, welcome back. So how you have to solve this question is pretty simple. It says we have 5 colors. So we basically have to represent 5 things with a pattern of binary numbers. And we know we just have 0 and 1 inside of binary to represent a number, right? But uh, if we just have 0 and 1, with just 1 bit, we could say 0 represents, say, green, and 1 could represent black. I'm just looking at the colors right here, green and black. Okay, but what about white, red, and blue? We can't represent these 2 colors with just 1 bit. Okay, let's try increasing the number of bits. Sorry, let me bring that back. Okay, so that's black. And let's say I increase the number of bits. First, we were at the number of bits were just one number of bits. Let's do 2 number of bits. So now we will increase the number of bits. 0, 0, 0, 1. But we can do more combinations now because we increased the number of bits. We can do 1, 0, and 1, 1. Okay, this is that same pattern that we see right here that we used to solve this addition problem as well. Okay, so yeah, we have this now. So now we can represent more colors. Black, we can do white as well. And what do we have? We have red. That's it. We can't do blue. Blue still remains. How do we do blue? Well, simply, we will increase the number of bits again. We will say 0, 0, 0, 0, 0, 1. Remember how to do 3-bit questions? I showed you how to make combinations when we were studying this. So we'll just add zeros here, and then we will repeat this pattern. Remember, this pattern is something you have to memorize, I told you. And we'll just repeat this entire pattern again. So I'll just write 0, 0, 0, 1. We know how to do this. This is memorized, right? 0, 1, 1, 0, and 1, 1. And then first we put zeros here. Now we will put ones for all 4 of them, simply. So now we have a combination of 1, 2, 3, 4, 5, 6, 7, 8. They wanted us to represent 5 colors. We can represent now 8. Okay, so the trick to solve this was that they needed to see if you understand how many bits to use to represent these colors. And we have to use at least 3 bits to represent these colors because with just 2 bits, we were able to represent only 4. What about the fifth blue? We couldn't do that before, right? So for doing blue, we had to increase the number of bits to 3. Now we can represent 8 bits. We don't have to use all the 8 bits. We can just use the last bit here. So now we can just put in this sequence over here. So starting with the 0, 0, 0, 0, 0, 1, 0, 1, 0. I'm just following this, okay? 0, 1, 1. And finally for blue, we have 1, 0, 0. Now, you could have said, I want this to be blue, okay? You can change around these sequences, but as long as each of these are nice and unique, no number is repeating, and they are 3 bits, your answer would be full marks for this. Um, your answer would get full marks for this question. Again, this side I've done only for explanation purposes. Um, please use uh, the box here to fill in your answer. Okay, let's move on. So another image is 3,579 pixels high and 6,128 pixels wide. The image is stored with a 32-bit color depth. The metadata for the image is 732 bytes, so they've given us the file size basically. Okay. Construct an expression to show how the file size um, in megabytes is calculated. Okay, you do not need to do the calculation. So basically, they're just asking you for the expression and not the calculation itself. Okay, they don't need the answer. They just need to see the expression, right? When you put all these numbers together, how do you multiply them, etc., etc. So again, pause the video and come back for the answer. All right, so welcome back for the answer. Now, I hope that you were able to do this on your own. Uh, but here is the answer. So firstly, we have to see what we have right here. Remember, when you want to calculate the file size of an image, you simply have to multiply the width of the image with the height and the bit color depth, and this should give you the um, size of the image in bits. If you want to convert that to bytes, you will just have to divide that by 8. Now, the additional information that they have given us here, which is something new, is 732 bytes of metadata. Metadata basically is just additional information about the image that is attached with the image. So what you have to do is once you calculate all of this, you simply have to just add the metadata. Okay? So whatever value you get out of here, you will add the metadata to it. Okay? So the metadata is 732. Whatever this value comes out to be, you will just add 732 to it. But you have to make sure that this value is firstly in bytes, because this is also, the metadata is also in bytes. If the metadata was expressed in bits, then we could have just added it to the bits value directly. But since it's in bytes, so we have to firstly convert our value to bytes, then we can add these two numbers. You cannot add bits and bytes together. That just doesn't make sense. The units have to be the same when you want to add something together. Just like if it was 3 kilometers plus 2 kilometers, we can easily add these. We can say this is 5 kilometers. But if it was 2 meters plus 5 kilometers, you cannot add this anymore because this is a different unit and kms are a different unit. So you'll either have to bring this down to meters, or you'll have to bring this up to kilometers so that both of them are the same unit. So basically, you just have to match the unit. If this was a box, this had to be a box. If this was a circle, it had to be a circle here as well. Right, so that's the idea. We're just trying to match the unit. Okay, So with all of that out of the way, let's start with our solution, inshallah. So firstly, we will note down and I'm going to do the calculations along with you here. Um, Actually, I think I'm going to do that down here. Okay. I'm going to just, for demonstration purposes, I'm going to use a calculator and I'm going to calculate the answers as well. Okay, so that you know how to construct the expression. Once you have the answers in front of you, it kind of makes more sense on why you built a certain expression. Okay, so that I just wanted to show you that, but then we will put in the box whatever we need. Again, I'm drawing this out here just for explanation purposes. You need to keep your answer within the box. All right, so firstly, and let me actually bring a screenshot of this down here so it'll be easy for us to reference as we are building the expression. I don't have to keep scrolling up and down that way. Um, Actually keep it down here. All right. So, firstly, it says we have 3,579 pixels high. So this is the height. So this is the height that they've given us. This is the height. Okay. And this is the width, because it says 600 and 6,128 pixels wide. So this is the width. So we can write either the width first or and then the height. We could also write the height and then the width. So because it's being multiplied, the order of the numbers really doesn't matter. So we'll start with, because I like to write width first, width and then height. So I'll do width first. I'll say 6,128 pixels. I'm going to write the units so we know that, actually I don't need to write the units right here. So I'll just say 6,128 pixels width. This is the width. I like writing the type of value in the parentheses so that we know we are keeping track of things. Sorry, not plus, we will multiply. That's how we build the expression. We learned this in our course. 6,128 multiplied by the width, the width will be multiplied with the height. So the height is 3,579 pixels. This is the height. Okay. Then we have the bit color depth. We're going to have to put that in as well. So we'll multiply that by 32. It says 32 bit color depth. So we'll just put 32 in here and we'll say bit color depth or color depth, whatever. Color depth. Okay. So now we have this major expression. And if you've built this expression up till this point, you would get 1 mark in your exam. And again, question is for 4 marks. So you would get the 1 mark right here. All right, next. What do we need to do next? The image is stored, okay, so the metadata is for the image is 732 bytes. Now, if we multiply all of these values together, we would get an answer in bits. I'll come back to the 732 bytes in just a second. Now, again, let me just for explanation, whatever answer that comes out of this, whatever answer that comes out of this, we need to add 732 bytes in here. The problem is the answer that will come out from here is going to be in bits. So we need to first convert that to bytes, and then we can add it to 732. So that's what we're going to do. We're going to calculate the answer first. So let's write the answer to step 1. Step 2 is let's calculate the answer. So I have the value calculated already, and I've done that in my calculator. Again, like I said, and like the question says, you don't need to calculate the values. I'm just doing this so that you get the concept of why we built a certain expression and why we are dividing it from we're changing it from bits to bytes and then adding it to the metadata. So it just becomes easier when you have a number in front of you. And then we'll talk about the expression as well, once more, just to summarize. Okay, so after you multiply the width, the height, and the bit color depth, the answer you will get, and I'm noting this down from my notebook, 701. You can try multiplying this with your own calculators as well. 7584. Verify if you get this same answer in your calculator too. Again, I keep repeating, calculators are not allowed in the exam. We're just using this for learning purposes. Okay, so we have this now in bits. Okay, this answer. Remember that whenever we did this and when we were learning this in the course, the answer comes out in bits. So now that we have this answer in bits, I also want to draw the conversion ladder right here. Let me draw the conversion ladder. Let me draw it with a different color. Let's do it with like this blue color. Okay, that looks good. Looks nice. So I'm going to draw the conversion ladder right here. So remember, we start with bits, then we move on to bytes. If you wanted to go further down, you could also say nibbles. Sorry, after bytes, you could say nibbles. But that's not going to be useful. We're not going to be using this a lot, so go with bits, then bytes, and then we can do kilobytes. Then we'll do megabytes, and then we'll do terabytes. We don't need to go beyond these. You can go on so on and so forth and build the ladder this way for the rest of them as well. Okay, so but for our purposes, this should always be sufficient. Most probably you're going to have to do it till megabytes and sometimes till terabytes, okay? Um, so now we have this ladder built in front of us. Now you remember when you want to go from a smaller value, the smallest value we have here is bits, but the bigger value, bigger than bits, is bytes. How many bits do we have in a byte? So a byte has 1, 2, 3, 4. Let me actually draw dashes. Easier. 1, 2, 3, 4, 5, 6, 7, 8. 1 byte. This is 1 byte. How many bits does 1 byte have? It has 1, 2, 3, 4, 5, 6, 7, 8 bits. Now we're going to put the 8 bits in here. So this is what a bit could look like, 0 or 1. It's one thing. So there are 8 bits in 1 byte. We know this, okay? Basic stuff. So let me write this in one line. There are how many bits in 1 byte? There are 8 bits. 1 byte has 8 bits. Okay, it's an 8-bit byte. We always say that, 8-bit byte. So if you want to go from bits to bytes, when we construct our ladder, this is the only place where we're going to do and 8. So when we're going from bits to bytes, we're going down the ladder. We're going from a smaller value to a bigger value. We will always divide in that case. So divided by 8. Okay? And when we want to go from bytes to bits, we're going from something that's a larger value to a smaller value. We will do the opposite. We will say multiply by 8. Now, why we do this, remember, when you think of division, when you take a big number like 1,000 and you divide it by, let's say, 2. When you divide something by 2, 1,000 divided by 2 becomes 500. So you see, the number became smaller. So when you divide things, things get smaller. When you multiply things, so if I said 1,000 multiplied by 2, what would I get? I would get 2,000. Now the number is even bigger, right? So it was 1,000 before, it became bigger. So same way, if I multiply it with something else, like multiply by 10, I would now get 1,000, 10,000, right? do that again. So if I multiplied that by 10, I would get 10,000. So you see the number is increasing when we multiply. The number is getting bigger when we multiply, and the number is getting smaller when we divide. So just remember that little rule when working with these things, when working with the conversion ladder. Okay, so that was just a little bit of a recap on that. Now, when you want to go from bytes to kilobytes, so you have to remember this little thingy here. Okay, you have to remember that. And the only other thing you need to remember is every time you multiply it by 1,000, sorry, by if you go from bytes to kilobytes, you're going to have to divide by 1,000. Okay, so what that means is 1 kilobyte, 1 kilobyte has 1,000 bits. Sorry, 1,000 bytes, not bits. Sorry. So we're now going from bytes to kilobytes. So 1 kilobyte has 8,000 bytes. That's why we are dividing by 1,000. Don't start saying we'll divide everything by 8 because that was only for the bits and bytes. Nothing else is going to use divide or multiply by 8. It's only for this top part of the ladder. Just remember, just memorize this conversion ladder. It's going to help you a lot. So we're going to divide by 1,000. We are going to go from bytes to kilobytes. If we want to go the reverse operation, we're going to go from kilobytes to bytes. We will say multiply by 8,000. Same way, we go from kilobytes to megabytes. We'll do divide again by 1,000. Whatever value in kilobytes we had, we're going to divide that by 8,000. And if we want to go reverse, we're going to multiply that by 1,000 instead of divide. We're going to multiply. Same thing here. Megabytes to terabytes, we are going to divide by 8,000. And if you want to go from terabytes to kilobytes, you will multiply by 8,000 again. So this is our conversion ladder. I call this the conversion ladder. This helps us to do our conversions. So we built our conversion ladder here, and this should help us in doing all of our conversions in this question. Okay, so now that that's in front of us, go back to our black pen. And solve the rest of this. So we had this in bits. Now we want to convert this to bytes. Remember, when you want to go from bits to bytes, you got to divide by 8, right? So you can see that right here. We divide that by 8. So we are going to do exactly that. We are going to divide this by 8. When you do that division, what do you get? I have that noted down, so I'm just going to write it here. The number we get is 77. I did this in my calculator again. 7728448. 7728448. That's the number that we get. Now this number is finally in bytes. It's not in bits anymore. We've converted it to bytes by dividing it by 8, thanks to our handy dandy conversion ladder, making it simple for us to do. Okay, now that we have it in bytes, we can now work with this extra information that they gave us, 732 bytes. We will add the 732 bytes here. The 732 bytes are going to be added here, after which the value will become, after adding the 732 bytes, it's going to become 8. Oh, sorry, this was an 877. My bad. This is the actual value. So 877 is going to become 877 29180. 29180. This is the answer that we're going to get after adding 732 to our original number. So again, this will be in bytes. Now, they said, the next part in the question says, construct an expression to show how the file size in megabytes is calculated. Okay, so we don't need bytes. We need the answer in megabytes. So we are currently over here. We need to jump twice to come to megabytes. So what do we need to do to come to megabytes? We need to divide by 1,000 once and divide by 1,000 again. So we will do that in two goes here, just so that you guys have an easier time understanding. So we're going to say multiply that by 1,000, and we can write here in parentheses so that it's easy to understand, 4 kilobytes, and the answer we will get is, sorry, not multiply. My bad, my bad. We will divide this. We will divide this. The answer that we will get now is 8772929.18, and I'm going to write KB here. Okay, kilobytes. After that, we will divide it again by 1,000. Why will we do that? This time we will do it for megabytes. You can see right here, we are currently on kilobytes now. We have the answer for kilobytes. Now we want to go to megabytes, so we will divide it by 1,000 once more. Okay, so divide by 1,000. The answer is going to be, now I think we can move this stuff down a little bit more so that we can have some more space. Yeah, so now we have more space. Hmm. So the answer will come out to be, divide this by 1,000, is going to come out to be 87.2, point 729. You can try this in your calculators as well. And this is going to be in MBs. We can round this number up, because after the point we have a 7. So when you go to a number beyond 5, like 6 or 7 or 8 or 9, anything above 5 after the decimal, you could round that up. I'm sure you guys already know how to round numbers up in your math classes. So 87 point, we can say here. So we could do that round up here. We could say 87.8, okay, or we could say 87.7, and we can round this up instead to 9. It's going to be a 3. Okay, so we can just round that up. So this would be 87.3 MBs would be your answer. Now I did all of this using calculators again, I repeat, so that we have an easier time understanding why we introduced a certain thing inside of the expression, why we added something, why we divided something with 1,000, why we divided something with an 8. All of that should now be clear with you, for you, when we did this conversion ladder. So now I want to write this just as an expression that will help you get your marks in the exam. So what you can write here is, you can simply say 6,128, that's the width, multiplied by the height. Sorry, I write the height first. 3579, that's the height, multiplied by 32 is the color depth. Okay, and actually want to write this to be a little smaller, so let me shrink that size down. We have some more space to write. I'll zoom in here, And then we had the divide by 8. So here we're going to say divide all of this with 8. Okay, and then um, divide all of this with 8, and then add 732. Okay, so this is what we did right here. We did this answer. We got it in bits. We did divide by 8. We got it in bytes right here, and then we added 732. So the answer that we got in bytes, we're adding it to 732. Okay, so that part is done. Now, whatever expression that we get, we need to divide all of that with 8,000, and then we need to divide all of that with 8,000. And when you have numbers like this, when 1,000 is like, when a fraction is being like, number is being repeated here, we could just write it in this format as well, 1,000. So we will multiply it, because we climbed the ladder down twice, right? Um, when we climb the ladder twice, we have to divide by 1,000 once and divide by 1,000 again. So that's equivalent to saying divide by 2,000, right? And how can we represent 2,000? We can also say 1,000 by 1,000, right? That's why we are just writing this right here. We could have also just multiplied these and said divide by 2,000 because you're making 2 jumps. If we made 3 jumps to terabytes, we could have said divide by 3,000 or terabytes, which could have written like this, 3 times 1,000. Okay, so that is how we're doing this. So this is the expression that will give you full 4 marks for the question, inshallah. Okay, with that out of the way, by the way, somehow if you were to able to calculate this answer, you would also get 1 mark. But that's not possible very easily in an exam that you have a time limit. You don't have to just solve this, you have so many other questions to do, right? So just construct this expression, show that you know how to do this, and that should be good to go. All right, let's move on to the next question. All right, so I hope you've paused the video, and if you haven't, pause the video, come back for the answer for this question that says, oh, sorry, I think I didn't read out the question first. So Alyssa is a music producer. Figure 1 shows the denary values of 5 samples of an analog sound using a sample interval of 0.2 seconds. So when they say sample interval, they're just basically talking about this time interval that we have here. It's going to go from 0 to 0.2, then 0.2 to 0.4. Every time there is a time interval of 0.2 seconds. You can see just add 0.4, 0.5, 0.6. So the 0.2 seconds are being added every time. Okay, so that's the idea. That's the time interval that we're doing right here. Now that we have that understanding of what they mean, sample interval of 0.2 seconds. Now this the first question is complete this graph, part 1. Complete this graph using the sample information from figure 1, this figure 1. This is the sample information we have to show the digital sound wave. So we're going to take the analog data that we have here. We're going to convert that to a digital sound wave. So that is very simple, very, very simple. So sample number 1 is going to be at denary value 1. So we simply need to plot the graph here. So sample number 1 is going to be at right here. Okay. And then the sample number 2 is at denary value 10. So we are going to, the second sample after 0.2 seconds is going to be at 10. So we're going to draw a line here. I'm going to join these lines in just a second. Then the sample number 3, which is after 0.4 seconds, it's this third column here, we are going to do 12. So you can see that I'm actually matching it from here. So up till this point, we have 12. So I'm just going to do 12 right here. Then we have sample number 4 is at 5. So 5's over here. Start from all the way there to a 5 right here. And then we have sample number 5, which is at 3. So we will bring the wave over here at 3 and draw a straight line. Okay, so now I'll just neatly draw this and join these lines together so that it becomes one wave. Okay, and this is looks like a binary wave, right? So this is the wave that we need to draw. Now, the second question that it asks us is, give a suitable label for the x-axis. This is the x-axis. What do you think this is representing, this x-axis? Well, it's representing time. It's representing the amount of samples that we have for a given period or a given interval. So we could say this is time. We could also say this is seconds. Okay, so we can say time. We can say seconds. We could also say for example, something like sample, interval, or period. Sample, interval, sample, period, anything goes. So I think the most suitable thing you can say here is time or seconds. I would like to go with time because it makes the most sense. Because this could have been in seconds, milliseconds, whatever. So you could get that wrong. This time is sufficient. Okay, y-axis. The second question is for give a suitable label for the y-axis. What do you think the y-axis is? Well, this looks like the intensity of the sound, right? So what is the intensity of the sound? What is a better word for it? Volume? Volume of the sound? Okay, we could say volume of the sound. So I'm going to write down everything that you can right here. You can say volume. Okay, that should be sufficient enough to give you 1 mark. Okay, you can also say, now I'm doing slash and the other answers that you could have written here. Volume, you could have said sound level. Volume is much better than sound level, right? This is also fine. If you're feeling like answering technically, so you could say amplitude. Amplitude basically means, remember that a wave, how high it goes and how low it goes. So that's the amplitude. So that's also kind of like the intensity of the wave, right? So you can see that the wave is only at a 1 amplitude here, then goes to a 10 amplitude, then a 12 amplitude up here. And then so you could also say amplitude. Okay, and yeah, I think that should be enough, right? So you can say volume, sound level, amplitude, right? So let's move on to the next question. So Alyssa uploads music files to her cloud storage. She compresses the files before she uploads them using a lossless algorithm. Give one disadvantage of using a lossless rather than a lossy algorithm for this purpose. So go ahead, pause the video, try and answer this question. So only for 1 mark, and come back for the answer. Okay, so the answer is pretty simple. Um, what is Alyssa doing? Alyssa is uploading her music files to the cloud storage. So she needs to upload uh, to the cloud. Okay, so her music files are going to go to the cloud. Maybe I'm not drawing such a good music symbol right here. Sure. So her music files need to go to the cloud. Now the problem is that she compresses the files before she uploads them using a lossless algorithm. So basically, she is converting it. She's keeping it to like a lossless algorithm, like a .wav, like a wave file. Okay. And instead of converting it to a MP3, which is a lossy algorithm, uh, but it reduces the file size, right? So what would be the issues that she could face? So you have one disadvantage of using a lossless rather than a lossy algorithm for this purpose. So Obviously, lossy means that we are going to lose some data. Losing data means we might lose some of the quality of the sound, but we will reduce the file size. That's the advantage. It might upload faster. Okay, it'll take lesser space. But when you work with a lossless algorithm, for example, like a WAV, like a WAV file, you are going to, it's going to take more space. That's the disadvantage. It could take longer to upload. Okay, so and it will take the advantage would be that it would be a better quality. And oftentimes you don't like I told you in the course, we don't even hear the differences in the quality of the sound because we don't hear certain frequencies anyway. So when those frequencies are removed, we don't really notice a difference, right? So um, yeah, sometimes the WAV and the .mp3 to us humans sounds the same. Um, so one disadvantage of using a lossless algorithm, we could say that upload time would take longer, right? Upload time would take longer. We could have also said something like it would become a larger file size, less compression, takes up. So I'm going to show you some more answers that you could have entered here. I'm going to put that on the screen. You can see, you can say uh, anything from transfer time would take longer. I said upload time would be longer. Larger file size, that's the disadvantage. It would have less compression. Okay. Um, it would take up more storage space in the cloud. Okay. It could use more of her data allocation. I think the fourth point is not very easy to remember, so you can use any of the ones that are simple. The idea is it will obviously take more space in the cloud. Next question says, explain one benefit to Alyssa of storing her music files in the cloud. Go ahead, pause the video, answer this question. Come back for the answer.